Hello students, welcome back to the class. And before continuing the classes today, let us recall what all we did in the previous class. So we studied about the total energy of a particle executing simple harmonic motion, and also we studied or we understood how to derive an expression for a time period of oscillation of a loaded spring. And in our today's class, we will be studying how to deduce an expression for a time period of oscillation of a simple pendulum. Now, we are going to find out the time period, how much time a simple pendulum takes to complete one complete oscillation. Oscillation means what? It is a to and fro motion. Now, continuing, if I consider a bob of mass m, so this is my bob here, and which has been attached to a spring of length L, and the bob would be of mass m. Now, what do? The bob moves, or I apply certain force on it, and it moves to a position P. So, if I consider this would be my position P in a time T, making a displacement. So, it is making a displacement, right? Changing its position. So, how is it changing its position? Angular displacement, I can say. It is making an angular displacement, that is your theta. Now, if I consider, yes, your bob is attached to one of the vertical, and there is an angular displacement happening, theta. So, the bob at this position P, here I can say the force acting on the bob at the position P can be resolved. So resolve the different forces acting on the bob. So I can say I am going to resolve the forces. And how am I going to resolve it? So always your horizontal in the sense it is straight to your what, your length of the spring, right? So if I consider the horizontal component, your force would be mg cos theta. So this is how I have been, or it has been resolved. And your vertical component, vertical to this one would be mg sin theta. And what is this mg? It is your weight of the bob, and it is w is equals to m into g, your mass, which is the force which is acting downwards. So this is how your force is being resolved, which is acting on the bob. And always remember that your mg sine theta, what is it, one of the component, that is your vertical component, mg sine theta, is nothing but a restoring force. So this is the force which helps, or which brings the bob to its mean position. So at this position, the force, which is it, which force, the vertical component, that is mg sine theta, brings back to its original position or mean position, I can say. So that is responsible, and that force is called as the restoring force. Hope you understood the whole story of your simple pendulum. And now if I consider or further deriving, I would consider torque. You can see torque is equals to force into displacement. Then what would be a torque? So here if I consider torque, it is a type of force which is also called as a rotatory force. So this is a force, that is a torque, which is responsible to move, or to move the body in a rotatory path. So that is called as torque, and this torque is equals to, the formula is given, force into displacement. If I consider the torque, it is denoted by tau, and this you can see the symbol here below this torque word. You can see the symbol over here, this one. This is your symbol torque, which is equal to, yeah, force into displacement, right? If I consider the force, what kind of force can I apply? Yes, obviously I have told you, where your torque is something that it is a rotatory force, right? So for a rotatory force, the force which I can apply is only your restoring force, which is it, mg sine theta. Why am I using only mg sine theta? So that is your restoring force. That restoring force is making obviously a rotatory path. Hope you got my point. So that is why I am applying a restoring force, that is mg sine theta, which is also responsible for rotation or rotatory motion of the bob. Into displacement, always remember displacement in the sense you cannot write theta here. It always tells you it is the length of the string or the wire which is connected to the bob. So what is displacement here? I would consider it to be L, that is the length. So considering or taking together tau, that is, always you have to call this as tau. Tau is equals to mgl sine theta. Now if I consider the restoring torque, so what is that? When I have considered this to be the torque and the force which I have taken it to be the restoring force, yes, now I can together say not restoring force, but I can say together restoring torque. So I can call this formula to be restoring torque, and I have written the formula as it is. Torque is equals to mgl sine theta. Now you can see a condition over here. If theta is very small, in the sense this displacement, if it is very small, then I can make sine theta to be negligible, and I can write it as only theta. You getting my point? If my displacement of the theta would be something like 1 degree or less than 1 degree, 0.5 degree, so it is very much negligible. If I consider the sine theta, by the rules, I can say sine theta would be equal to theta. Children, there's a question for you. If I consider, if in any of the cases, if I have got cos theta, and in that cos theta, if I consider theta to be negligible, can I write it to be as only theta? Cos theta is equals to theta? No, it is cos theta is equals to 1. That is the condition. So if I consider the sine theta is equals to theta, so if I consider cos theta would be equal to 1 when my theta is negligible. And if I consider tan theta in any other cases, it would be theta itself. Only when there is cos theta, when at that case the angle is a minimum or very negligible or very small, then I can write cos theta is equals to 1. And rest all sine and tan would be theta itself. My restoring torque would be now to be as sine. I have taken it out and written only theta here. So tau is equals to mgl theta. Now you can see there is moment of inertia. So what is that moment of inertia? Hope you have learnt what is inertia. It is the ability, if I consider only the inertia, I can say it is the ability of the body to be at rest or in a uniform motion unless and until any force is applied on it, right? So if we are going in a bus, what would happen? Until a person or the driver applies a certain brake to the bus, what happens? You will be sitting still. When he applies the brake, then some force is acting, then you move front. So these are the things. Now if I consider moment of inertia, what is the moment of inertia? It says that opposition offered by the body. So a body is offering resistance. What kind of resistance? If I consider during the simple pendulum, what kind of resistance a body can offer? It says that, please understand, or else write down, opposition offered by the body during rotatory motion. So if I consider this pendulum, so this object is offering some resistance for the rotatory motion. So that is called as moment of inertia. Now, if I consider the formula for moment of inertia, you have got that I is equals to mass into length the whole square. So finally I can write I is equals to ml square. This is your moment of inertia's formula. Next, continuing, I have angular acceleration. So what is that angular acceleration? So acceleration happening angularly. So it is making certain angle. So if I consider the angular acceleration, the formula given for angular acceleration is A is equals to tau divided by I, that is moment of inertia. So where previously we calculated moment of inertia ml square, and what is tau? It is mgl sine theta, and sine theta became theta, then your tau would be mgl theta. So the value you are substituting here, right? So why is this a negative sign here? Why did you get the negative sign? So before going to the negative sign, I would tell you, substituting tau value here and I value here. And what is this negative symbol? It is the restoring force, which is opposite to the displacement, right? So if I have a pendulum, I would displace in it this way, and the restoring force is in this way. So this is what is called. And if I consider further, I can what all the things I can cancel here is m l, right? So one l remains, and I would get a is equals to minus g theta divided by l. Now if I consider, okay, in the previous lecture I have taught you how you got a acceleration due to the simple harmonic motion, a particle executing a simple harmonic motion, right? If I consider that, you would see a is equals to minus omega square. Actually this is y, children, make a note of it. This is not theta, y. Howdala, I had made you to write it as y, which is your displacement. Please correct it. It is not theta, this is y. So understand this properly. This position, this point, which is called as a is equals to minus omega square into y, is something that acceleration of a particle executing simple harmonic motion. So why have I taken this when I have calculated this equation? Always let me compare these two accelerations. Okay, so simple harmonic motions and this one. So when I compare this, here y, okay, the displacement happening, and what kind of displacement is here? It is angular displacement. This displacement is normal displacement. Okay children, so I am comparing these two equations. When I compare these two equations, what in common I would get? These two are theta and y. Please do correct this. This is y, not theta. So if I compare this one, this is the displacement, this is your acceleration, and what are the remaining things here? I have taken it to be as common, that is your omega square. I have taken the omega square here is equals to g by l. I have taken here, and negative sign will get cancelled. Now what is that? Rearranging your equation, which you know very well. Omega is equals to what you're doing the square, you're taking the root on your right hand side. And what is omega in your next equation? So here you can see that 2 pi f right, which I had given you already in my previous lecture. Omega, the value of omega would be 2 pi f frequency, and how frequency and time period are related. F is equals to 1 by t. F equals 1 by t, right? So that is what, in the place of f, I've substituted 1 by t here. So you would get 2 pi by t is equals to root g by l. And later on, to make or get the time period t, I have shuffled or rearranged my equation, and I would get it as t is equals to 2 pi root l by g, length. Okay, so if I consider this equation, this is your time period. This is your time period for oscillation of a simple pendulum. So hope you understood how to derive a time period of oscillation of a simple pendulum, which will be arriving for 5 marks. Next, going to another topic, that is your damped oscillation. So what is that damped oscillation? Now, damp, in the sense, the meaning for damp is suppress. So what is that? Suppress, ಕಡಿಮೆ ಆಗೋದು, suppress ಮಾಡೋದು ಒಬ್ಬರನ್ನ, ಹೌದಲ್ಲ? So if I consider suppress, damped oscillation, it means that in the definition you can see the oscillation in which the amplitude keeps on decreasing due to the force of opposition. So what is happening? Your oscillation in which the amplitude, it is the, what is amplitude? It is the maximum displacement, right? So that amplitude, the displacement, keeps on decreasing due to the force of opposition. You should understand it very carefully. I'll be giving you an example. Now going back to my slide. So if I consider this to be my pendulum, okay, so what would I do? I displace it to the maximum, and where my amplitude is maximum, ಹೌದಲ್ವಾ? ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಜಾಸ್ತಿ ಆದರೆ ಆಂಪ್ಲಿಟ್ಯೂಡ್ ಕೂಡ ಜಾಸ್ತಿ ಆಗುತ್ತೆ, and it would come back. So it is going, so coming, and what is happening at certain time, you can see that your oscillation gradually reduces and comes back to its mean position. Why is it? Because of, it is because of the opposition offered. What kind of opposition? It is the air resistance. ಏನು ಗಾಳಿ ಇದೆ, so air is there in our surroundings. So because of that opposition, you can see that there is a damped oscillation, suppress, and there is a decrease in the amplitude or displacement, decrease ಆಗ್ತಾ ಹೋಗುತ್ತೆ. So this is called as damped oscillation. So you can see in this graph that as your amplitude, that is your displacement, is more, and as it takes time, according to the time, so it is more here, decreasing, it finally decreases and comes to its main position. This is called as damped oscillation. And what kind of force of opposition? So I can say air resistance. So the air also may offer certain resistance. And one of the students of first PUC had asked me a question: what would happen to a pendulum when it is kept in a vacuum? Space ಅಲ್ಲಿ ಇಟ್ಟಾಗ ಏನಾಗುತ್ತೆ? There the amplitude would be same. There is no damped oscillations in the vacuum. Why is it? Because of there is no force of opposition, there is no air resistance offered in the vacuum. And you can see there, when as the pendulum starts oscillating, it will be oscillating forever, because there is no opposition. Only unless and until there is a opposition offered, until then it will be oscillating with the same amplitude given. Same amplitude, ಎಷ್ಟು ಆಂಪ್ಲಿಟ್ಯೂಡ್ ಕೊಟ್ಟಿರ್ತೀನಿ ಅಷ್ಟೇ ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. ಯಾವಾಗ offer ಆಗುತ್ತೆ when the force of opposition is offered, yes, obviously here you can see there is decrease in the amplitude. So this is all about today's class, children. In the next class I will be teaching you about forced oscillation and resonance, and also few problems on oscillation. Thank you, children.